So this building has 5 floors. So I added one more floor. So we'll consider wind load also acting on the same structure, and we'll for this problem we'll consider the magnitude of the wind load is equal to 1 kilonewton per meter squared of the facade area. And generally, when you do the calculation at a height of around 5 floors, you'll get about 1 kilonewton per meter squared. So I will consider that particular wind load is effective at all floors. So these 16 meters. So 16 into 3.6, 57.6. So I'll consider the wind load as well at this level. Assign Wnex global X direction 57.6. And in this direction, I will apply the wind load at 2 locations. And the total length of the is 4.5 plus 5.5 plus 4.5. It is 14.5 into 3.6. So I'll get 52.2 divided by 2. So I'll apply joint force of 26.1. Sorry, wrong. Assign joint load forces. This wind Y. So these loads are there. And if I go to the lower level, zero, view, assign joint forces, view, it's in that level, and display the next, that's in that direction. Okay. So now I will go to the lower level. And allocate the supports for the structure. Later I'm going to change all this, but for the time being, to complete the analysis, I'll simply say all the supports are fixed for the time being. And with all this information, I can look at this in 3D direction and then select all the members and replicate it at 3.6 4 times and create the building that you want to do the foundation design. So when we come to this level, so we have all the loads acting on it, but they are all basic loads. So you have to create the load combinations so that we can decide the combined effect of different loads. So when you are doing modeling for Euro codes, so we have to consider different load cases. One is the building is there and the wind load is maximum 1.5 times WK and the self weight, that is 1.0 GK. That is the first case, case 1. Then you have to consider the possibility of this being remaining as dominant and these loads also acting then there's another possibility. All these loads 1.35 and this way 1.5 WK. But in addition to that, we can get 0.7 times 1.5 times QK. That is the imposed loads also acting. And this gives a value of 1.05 times. And we say this case 1. And if you look at these two cases, you can see this is going to be more critical. So no need to worry about this particular case. So we can say this case 2. And then we can get another case. That is the imposed load becomes dominant 1.35 GK, but the wind load becomes the secondary variable load, and that is 0.5 times 1.5 times WK. So you'll end up with 0.75 WK. So these are the loads that will act, and we have to consider the loads in X direction, and we have to consider the loads in Y direction, X direction and Y direction. So each of these cases with wind will get two cases, X direction and Y direction. And in addition to that, we can get minus X direction, minus Y direction. So you can get different cases. And in addition to all this, we generally may not be more the worst, but we generally create 1.5 QK, 1.35 times PK case as well. And we say it's combination 4. So this combination 3. So you get, so these not case, combination 1, combination 2, combination 3, combination 4. And each combination will have wind load. If it involves wind load, it will have 4 different cases. But in this case, no such situation because it's only the vertical loads. And in addition to that, we can also get service combinations. Each of these can have a service combination. One, and X direction. And if it is in the reverse direction, I would say XX direction. So X means the positive direction, XX means negative direction. And if you have S, that is a service combination. And if you don't have any S, it's the ultimate combination. So this way we can create a number of load combinations. So you can, I will not create all the combinations, but I will create only one or two just to show you how it's done. And I have a template that I have already made. I will make use of that by opening a new file. So you can add a combination. Combination 1 in X direction will be, so before you do the combinations, and you have seen that, you know, for all the loads, we have created only the basic load case, basic load pattern, and we are not created anything to represent the loads on the slab. So if you consider the loads acting on the slab, that is the place where we get most of the loads acting. The first load that we have to consider is the self weight of the slab. And self weight of the slab is 0.15 multiplied by 25, and that is 3.75. So we have to say unit slab 3.75. So that is the self weight of the slab. Okay. And then add a new combination. Oh, we can see. Add a copy of the combination. You can say slab finishers, and the magnitude is 1. I can say modify and add the combination, and it is slab services. It's 0.5. Modify. And then copy slab finishers, services, partitions. Continuity is 1. Then we have to add slab live and 2.5. Modify. So we have all the combinations, all the loads that you need for combinations. Then add new combination. Combination 1 in X direction. And we have to consider the dead weight of the structure with 1.0 GK and 1.5 WK. And then we'll have the self weight of the slab. Then we'll have finishers. Then we'll have services. Then we'll have partitions. Then we'll have the facade. And then we'll have the wind acting in X direction with 1.5. And So similarly, you can add a copy of the combination, and we can say combination 1 XX, and here you just go there and say it's minus 1.5, and in Y direction also add a copy of the combination, and combination 1 Y, and here we go there and say win Y, modify, now it's done, and add copy of the combination 1 YY, just go there and say win Y is minus 1.5, modify, and then we can go to the next one, add a copy of the combination 2 X, and all these will be 1.35, modify 1.35, modify 1.35, modify, and so similarly I can create combination 2 XX, here you get minus, and then I will not create the others, but I will go to the combination, the service combination. So you get service combination. So this one had a copy of the combination, and this is a service combination. Service combination 1 will be all this, but this will also become 1. Service combination 1 X. So similarly, you can create a service combination XX, and then so similarly you can create all the service combinations, and just to show you, I'll create the service combination 3X as well. 3X combination 3 has both dead and live loads. So I will delete this, and I can say sap live 1.5 add, and I can also say winx 1.5 add, but this has to be modified to 1.05 because the dominant load is wind. So this is secondary, so this has to be 1.5 multiplied by 0.7 for the live loads. So that is combination 3X, and then similarly we can add combination 3XX as well. I have made a small mistake. Let's give it. Actually, I said combination 2 will be the 1.35 GK plus 1.5 WK plus 1.05 QK. So I will actually we'll modify that. So 2x is delete, and slab live 1.05 add, and then win x is 1.5 2x, and so the others have to be changed accordingly. And combination 3x is slab live is 1.5 modify, win x is 0.75, and that's what I have drawn. So what I have drawn is this combination 1, which has only the dead and wind. Combination 2 has 1.35 GK, 1.5 WK, and 1.05 QK. Combination 3 has 1.35 GK, 1.5 QK, and 0.75 WK. So those are the combinations. So here you can see 1.35 GK, 1.5 QK, and 0.75 WK. Okay. I will delete this, and then I can add combination 3XX will be minus 75 modify, it can go on, and then finally I'll get combination 4 will be dead and live loads only, no wind load. And then I also want to highlight another fact. Now when you look at the live loads, when you have a multi-story structure, a certain reduction in the live load is allowed. So if you have more than 2 floors, you can deduct 10% of the live load. If you have more than 3 floors, you can deduct 20%. So when you have about 5 floors, so in this building, there's a possibility of deducting up to 40%. So instead of 1.5, then for the live load, you can actually use 0.6 times 1.5. So you get 0.9. So if you, in British courts, they allow this reduction in live load. And the reason for this particular reduction is that all the live load values that we specify has an allowance of about 50% for the dynamic effect. So if the actual live load is 1, what is specified is 2. And this dynamic effect is important only for local effects, not for the global effects. So because of that reason, the codes allow us to do a small reduction in the live loads. So in this 5-story building, we can go up to about 40% reduction in the live load. But in this particular example, I think I have ignored this live load reduction. So I will not consider the live load reduction. So I'll just keep it as it is. And so if in addition to this combination 4, I will also define a service combination 4, and that is only due to dead and live loads. So what I do is I will cancel this, and for that it's easier for me to copy from this one. So service combination 4 will be all this, and in dash delete this, and I have to add slab live also, and in the slab live also I can have this 0.6 factor if I'm going for live load reduction, but in this particular example I have not gone with live load reduction. So basically this way you can have all the load combinations. I have not defined all the combinations, and in addition to that we have to do a small modification, and before doing the modification we have to see whether we are on the right location. Yes, here you can see if I say deform, these are 3D view. So because we have a certain depth for the foundation, so I can increase the downflow height by about 0.5 meters vertically. So I will move all this by 0.5 meters vertically, and if you are doing that, the moment you do that, you can change the grid as well, and here you will go to the spacing again, and here you will say it's 4.1 meters. So here you can see the ground floor has a height of 4.1 meters, and the moment you say okay, sorry, I have done a mistake earlier. Just I think I have moved all these members. I should have moved only the support, but unfortunately I have moved the whole thing. And define. Move by 0.5 face. So I should have moved only this. Move by minus 0.5, and then say so this spacing is 4.1. It starts at minus 0.5. 4.1. Okay, now it's okay. So it starts at minus 0.5, it goes like that. So the ground floor has a height of 4.1 meters, all the other floors are 3.6 meters. So I'll just save it and then I'll open the proper one, that is B2. B2, open B3. Has it got all the load combinations defined? Yes, it has all the load combinations defined. So basically, open. So this is BU2. And once you create all these load combinations, we can define the envelope as well. So you can add new combo. And we can, if you want, if you are interested in getting the envelope in X direction, you can say add new combo. So you can say envelope in X direction, and you can add all the combinations that we are dealing with X direction. And so 2x. So all those combinations can be added. Combination, you can add combination 4 as well, though it has no direction. So these envelope X, but here you have to say it's envelope. You can't keep linear, you have to convert it to envelope here. Then only you will get the envelope due to all these effects. Otherwise, you will get the addition due to all these effects. So you are looking at what are the critical ones out of these combinations. So you have to go with the envelope. And then you can also create the envelope in the y direction. And again, you have to say envelope. And all those combinations in y direction can be added. So I don't have many to add because I have not created the combinations in y direction much. And then I can also create another combination, and that is the envelope in xy. Just the maximum in any direction. So what I have to do is I have to say it's envelope of x and envelope of y. And that way I can create all the envelopes as well. So save, and then I'll open the same model. Say we'll say model 4, and same model, but this height has not been changed. We can do it later. And then we'll open number 5. It has also created. So I will not go back to model 4, B4. So basically it has everything. And so if I look at it 3D this way, 3D. So what I have to do is just move all these by 0.5 minus 0.5 the other hand, clear selection. I'll move the whole building by 0.5 meters upwards. And then go to the change the grid to spacing 4.1. So the grid is also sorted out. And if you look at the load combinations, you can see slab self should be 3.75. And slab finishers, as you have seen earlier, slab partitions seen earlier, and slab live 2.5, and all the combinations are there, and then all the service combinations are also there. And here you can see slab live is 0.7 because 70% contribution, and when it comes to wind, you can see wind is 50%. And then there are service envelopes and combination 4, service combination 4, and envelope X, envelope Y, and envelope XY, and service envelopes X, Y, XY. Service envelopes. So I have all the service combinations and ultimate combinations. So what I can do is I can just analyze this to see what the type of loads that are acting through the columns. So I can just analyze this and see what the type of loading that are acting along the columns. So what I do is I'll ask it to analyze it. And I can display. I can select one of the frames. Then it shows the coordinates showing today 8. It's showing now. So this y is equal to 8. So that is one of the middle frames. So if I look at this, so I'm looking at grid 3, and I can ask it to display the, if I want, I can just select one combination and ask it to show the bending moments, display bending moment diagram. And if you want, you can just have a look at the moment values 64, 39, and so on. And this is only for this combination, but on the other hand, you can also look at the envelope XY or envelope X, because we are looking at a frame in the X direction. So we can say, find the information. And in addition to that, we can also see what the type of axial loads that are acting. And here you can see the axial load has a maximum value of 650 or 671 here at the bottom, and 1257, 1257, and 671 according to the envelope. But we are now interested in the foundation sizing. So that's why, we analyze the superstructure first to see the type of loading that are coming. So what you have to do is, rather than looking at all that, we have to look at service combination. So just to keep things simple, I will look at a load combination, not the envelope first. So I'm looking at a certain combination, and that is the combination giving the effect of dead and live loads. And I'm not interested in the deformed shape, I'm interested in the forces. So envelope service combination for axial loads. And when I look at the axial loads due to service combinations, I'll get 458, 894, 894 and 458. So those are the values that I'm interested in resisting. So on the note, I have shown you how to get all these unit load effects, facade, then the unit slab converted to sub self weight, but I have considered this as 3.75, not 3.6. And combination, then the combinations. So different combination values are given. And then the service combination for giving the permanent effects and variable vertical load, and that is due to the slab live load. And then getting a model like this, 3D view, and the forces, 458, 488, 488, and so on. So those are the forces, but I think I might have to do a small change here, and that is I might have to be consistent, 460, 193. I might have to change a bit, and that is because the knot is based on 3.6 for the slab self weight. I will reverse back to 3.6. Otherwise, this model may not be compatible with 3.6. This model may not be compatible with the values on the note. So I'll just do that change and save. And now you can see the values are 350, 453. Display. $454, 888, and that actually tallies with the values given in the note. So I just made a small change so that note and the model will be the same. So if you look at the foundation, we have to design the foundation to carry all these loads. So the addition of loads will be 458 into 2 plus 888 into 2. So the addition of all that will be 2692. And if you look at the model, again, you can see the coordinate here. The coordinate here is 0. The coordinate is 14.5. And the column has a size of 400 by 400. So I will consider that the total length of the foundation is 14.5 plus 0.2 into 2, 14.9 meters. So the total length of the foundation is 14.9. The total load is 2692. So 2692 divided by 14.9 divided by 120, that is the bearing capacity, gives a width of 1.5 meters. Gives a width of 1.5 meters for the foundation. So I can actually find the width of the foundation. But before we find the width of the foundation, we have to do another small adjustment. And that is, that adjustment is, we have to see what is the net bearing capacity. So basically, by doing the superstructure, we can find the loads on the columns. And when you know the loads on the columns, you can work out the total load on the foundation, which is going to be a combined footing of inverted T type. So the total load transferred is 2692 and it acts over a length of 14.9. So we have to now see what is the net bearing capacity. And net bearing capacity is the allowable bearing capacity minus the self weight of the foundation. So because we are going to have an inverted T, we may have a depth of about 0.9 meters to 1 meter. And we will have an inverted T of about the flange of about 0.3 meter thickness. So I consider that the weight of the foundation is equivalent to a height of 0.5 meters. So if it is equivalent to a height of 0.5 meters, then 120 minus 0.5 into 25 is the density of concrete, 107.5. So the net bearing capacity will be 107.5. So if I divide 2692 by 14.9 and 107.5, so the answer is 1.68 meters. But because this is an inverted T-beam that we are going to design, under these heavy loads, sometimes you might get a slightly higher pressure, or sometimes these places you might get, because we are ending the beam here, we might get a slightly higher pressure acting at these places. So to allow for all that, I need only 1.68, but I will select a width of 1.8 meters for the inverted T. So I will select an inverted T of this type, 1.8 meters of width, 300 millimeters of thickness, and overall depth of 1 meter, and also the width of the web of 450 millimeters. The column size is 400 by 400, which means the foundation reinforcement can be sent on the outside the column reinforcement. So when you're sending these outside the column, the beam reinforcement, outside the column reinforcement, you might have to consider providing 1 or 2 links within the column as well. So just to make sure that this reinforcement is retained at the correct place. So I will consider the size of about 450 millimeters for the web of the inverted T-beam. So that is the size of the T-beam. So now we can create the T-beam and then see how we can apply the springs as well.